Okay, so this is Unit A. I guess you could scratch that 2 out. This is Unit A, Kinematics. We got some graphs, we got some spark timers, and we got some formulas on this page. This is just a title page. So we will be working with graphs. You can see some of those graphs are stationary, some of those graphs are linear positive, also linear negative. So we'll have to interpret that. And also you can see there's a red curve that is not linear. So that would represent acceleration, and we'll talk about that in this unit. These are the formulas from your data sheet. So those are called the kinematics equations. And then up here, up with these dots, those are examples of spark timers, and hopefully we can get in the lab and do some work with spark timers. So those dots are like little sparks that burn the paper. There's some carbon in there. It burns the paper every like 1/10 of a second, and then you can model motion. Okay, so representing motion. So to quantify motion, we need to know where and when. So distance and time. Okay, not all where means the same thing. So basically you have two. Position and displacement are essentially the same. So those two are essentially the same. And those two are both ideas related to the vector. And not all speed means the same thing, or not all motion means the same thing. So velocity versus speed. So velocity is also a vector. And this comes from Science 10. You should be already aware of what a vector is. So does anybody know what a vector is? It's a quantity that has what? Size and direction. Good. So magnitude, that's how much, and direction, which way. Okay? So a vector has two quantities. How much and which way. That's like a layman's way of explaining it. How much and which way. So the 7-Eleven, it's about a couple blocks north, roughly. 112th Ave is more blocks, about 5 or 6 blocks south, right? So a vector would be how much and which way. So here's the formal definition: size and direction. And displacement, velocity, and force and acceleration. These are some vectors that we'll become familiar with. There's obviously lots more. These are some usual suspects. And quantities that don't have direction, only size, are called scalars. Okay, so is there any questions about the difference between magnitude and scalar? Or pardon me, scalar and vector. Okay, so let's do some examples and you should be okay with it then. Nothing? Okay, so displacement versus distance. Distance is how far something moves, regardless of the starting point. Okay, so if I start at home, drive to work, and then do my job all day and then drive back home, I've traveled a lot of distance, haven't I? I had to drive all the way to work and then I had to drive all the way back. That's a lot of distance that I've covered. However, what's my displacement? 0. Good, because I ended up exactly where I started. So displacement, it keeps in mind direction, while distance does not. Distance is just a number. How far have you traveled? Whereas displacement, it takes into consideration position. Okay, so highlight position for displacement. And then of course the symbols would be d and then d bar. Now sometimes I get a little bit lazy with my symbols, especially if I'm writing formulas over and over again. So just keep in mind that are you interested in displacement or are you interested in distance? And then typically, just to make things easy, we just define a certain set of rules. So for example, I might say that if this is my middle, then I'm going to put positive values to the right and negative values to the left. Okay, and that's just a convention. It doesn't have to be that way. You could definitely say that the right is negative and the left is positive. You could definitely do that, but most people don't. And if you're doing a displacement vertically, you can set a spot for 0, and then up would be positive and down would be negative. And of course, you could have down being positive and up being negative, but you're probably just going to confuse people, and you probably will just confuse yourself. Okay, so let's take a look at this picture. So in terms of distance, who traveled the greater distance? Yeah, Alan traveled the greater distance. Alan is greater than Eva. Because he does this crazy winding path that takes a look at this whole rectangle. He's all over the place, whereas Eva is just left to right. You can see that that line is shorter than Alan's line. If you stretched out Alan's line, it would be much farther than Eva's line. Now in terms of displacement, who traveled farther? They're equal, good, because they both had the same start point and end point. They've essentially displaced the same amount from the west gate. So it's the same displacement. Because in terms of position, they're both 100 meters east of the west gate at the end. Okay, so I'll let you guys try this example. This one's not too bad, and then we'll talk about it. Okay, so let's try this example. Let's see what we had. What did you guys calculate for distance? 1800? Good, so you got 400 plus 500 plus 400 plus 500. Is that it? I agree. Okay, so 1800 meters. Now, in terms of significant digits, what do you notice about the diagram? How many significant digits? 3. So, while this is a simple example, you might forget about significant digits. We would have to convert this to 1.80 times 10 to the 3 meters. Okay, so it's just a good habit to get into. Ultimately, if you were able to solve for 1800, that's 99% of what's important, but we got to be careful. Now, in terms of displacement, you didn't know how to do this one? So for displacement, because it's two-dimensional, and we'll talk more about this later, you have to look at both dimensions separately. So let's take a look at dx. What is the displacement in x? 400 east plus 400 east. Do you agree? Remember, you have north, south, east, and west. Remember, east is Toronto, west is Vancouver, north the Arctic, and south the United States. So if you're looking to the right, that's east. So in total, you have 400 plus 400 for a total of 800 meters east. That's the displacement in x. Now, what's the displacement in y? 500 north and then 500 south. So those work against each other. Do you agree? Yeah, so my north would be positive and my south would be negative. Notice my east is positive and my west is negative. So when I went to add them up, I added two positives. Adding two positives, and I end up with positive. Now here I'm going to be adding 500 north, and then I'm going to be adding 500 south. So I end up with a displacement of 0 meters in the y direction. So my displacement is 800 meters east. That's your final answer. If the displacement in y was non-zero, you would have to do a Pythagorean theorem and do a resultant vector. And we'll talk about all that when we get to vectors. This kinematics unit, the first couple weeks is all one-dimensional, and then we move into two-dimensional problems. So for example, you're driving a boat on the river north, but the river is flowing west. And then you'd get pushed off on a course that's a hypotenuse. And we'll talk about that when the time comes. But for now, this is all one-dimensional stuff. Okay, so adding vectors in one dimension, we're going to use arrows to represent vectors. And arrows will have a tail and a tip. Okay? So arrows have a tail and a tip. Now the magnitude of the arrow is usually indicated by the size. So if you look at the vectors down here, look at 18 meters, that vector. It's about 3 times bigger than this vector. Now, this is not a perfect thing. You don't have to like get out your ruler and draw a scale and make sure it's perfect. You'd be here forever. And then you'd probably still have mistakes. So what you're going to do with your vector diagrams is just try as best as you can to indicate some idea of magnitude with the size of your arrow. And we will always add vectors tip to tail. Notice that this tip is touching the next tail. This is how vectors are added. And that is crucial, okay? So if you take a look at the addition of these vectors, you can see you've gone 18 meters east and then 6 meters west. Altogether, you've displaced 12 meters east, because 18 plus a negative 6 is a positive 12. Your distances, you just add them. Notice the distances are the same, but the displacements are different. And here's the sign convention we talked about in the last slide. Pretty straightforward. And the other thing is, like, I would rather than think about like this arrow should actually like be on top of that arrow because it's all in that same dimension, but it just for neatness you just put it a little bit below. Like this arrow should be on top of that arrow, but you would never be able to make sense of it because it does kind of look like you went south a bit, right? You went south a bit, so just that's for clarity. Okay, so you guys can try this one. Okay, so what you guys get for some answers here? Lovely, 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 lovely. Okay, so I know this stuff can get a little bit tiresome, but I recommend that you put on a sign convention. It's just a communication piece. So if I travel 250 meters east, that would be to the right, and 350 meters west, that will be to the left. So then I can draw my vectors. And you can use a ruler if you like. And this guy is 250 meters. And then he goes and switches direction. So if I'm 250 meters east, I started here, ended here, right? So where would I start the next vector? Where I ended. Lovely. And is it the same size? Is it smaller? It's a little bit longer. And I don't know exactly how long. It doesn't matter. I just need to have some indication of that. And there's 350 meters that way. Now mathematically, for distance, you don't care about sign. It's just 250 plus 350. And you end up with this 600 like she said. And notice how I'm lazy with my units until the end. Okay, I'm not lazy at the end. I am lazy in between. So, and displacements. And you can see I don't really care about the speeds right now. We'll talk about speeds in a second. For this one, I prefer these square brackets. The 250 is east, so I can leave it positive. And you're always adding. Okay, just keep that in mind. You're always adding. Just sometimes you add negatives. And those square brackets are just something that I've grown accustomed to. You don't have to use them. That's just something I've decided I'm going to use. So 250 minus 350, and you get this minus 100. So in other words, it's 100 meters west. Okay, so communication is huge, neatness is huge, organization is good, sign convention, all this stuff. So these are all good habits to get into. Okay, so go and find your first homework assignment. And then it won't take you that long. We'll have time for some harder stuff in a bit here. All right, find this page, and remember it's in the other book, yep. And these are graphics taken right from your textbook. So I follow the textbook, but the order is jumbled. Okay, so I follow the order of the EPSB workbook. I follow that order. However, the textbook jumps around. So often my slides will have stuff taken from the textbook. So you have the textbook as a reading resource. They have similar examples to me, and they got all this extensive writing that you can read. And to really get an understanding, a strong understanding of physics, you need to be reading, you need to be doing homework, and you need to be obviously in class. And there's also labs. So physics is a very well-rounded science, and there's lots that you have to take, lots that you have to do if you want to achieve mastery. It's not like math where you can just sit there and take in the math and practice it and you'll get good at it, where math is mostly a skill, and especially in high school it's an algebraic skill. There's a little bit of problem solving, where physics is so many different things going on. Anywho, let's take a look. You have a position time graph. You can see position is graphed vertically, time is graphed horizontally. That is a pretty standard. So you can see that distance, in this case displacement, depends on time. Calculate the slope of the line. What does it represent? You guys have been doing this in the lab, and these data points are exactly the line of best fits. So you can just simply do the entire line. What's that change in y? 5 meters divided by 5 seconds, and you get 1 meter per second, which you can see is quite obvious. 1 second over, 1 meter up. 1 second over, 1 meter up. And that meter per second should stand out to you. What does it represent? Speed, but in this case, because we were dealing with a displacement, It's not speed, it's velocity. So we have to attach a direction to this speed. What is the direction of this speed? Well, we take a look at the graph. The graph says that positive values are to the right. So this is 1 meter per second right. Okay? You guys okay with that? So position time graphs. Motion can be easily represented by position time graphs. You will have these on your exam. They are position versus time. You can see independent and responding. So another word for independent would be the manipulating. And another word for responding would be the dependent. So position depends on time. How far along in the journey are you? How far along in the displacement are you? Meter per second is your standard unit. And in red there, you can see there's 3 operations that you can do with these graphs. Obviously, you can read the graph, find points, find coordinate pairs. For a certain x, you have this y. For a certain y, you have this x. Okay, so a lot of this, just reading coordinate pairs. Also interpreting. You have to be able to interpret the scale, interpret axes. So especially if there's positives and negatives. So like if you have a negative velocity, what does that mean? If you're below the x-axis on a velocity time graph, what does that mean? So that's what it means to read the graph. And then finding slope and finding area, these are the 2 things that you have to be aware of. These are massively important. Finding slope and finding area. And I will show you when and where as this unit progresses. So uniform motion. Uniform motion, just put this. What does this mean? Acceleration is 0. That means you can be moving, but your speed is not changing. Okay? So uniform motion, these are best displayed by linear graphs. Linear, and of course these are position time graphs. The position time graphs are linear. Now they're showing you a in this diagram here, this is an object at rest. You can also be moving and have uniform motion. And this is a key word here, uniform motion. You're moving, or you could be at rest, but essentially you're moving but not accelerating. So an example of this would be like, say I was dog sledding, and I was whipping those dogs. I was like, hi, go, and then we're going. You know, if I start from rest, I'll have to speed up, so I'll accelerate for a little bit. But then there's probably some spot where like the friction in the snow matches the pull from the dogs, and I just travel at the same speed. So I'm moving without accelerating. That's uniform motion. And you can like ignore like that first couple seconds where I accelerate into the uniform speed. Okay, so at the end of a school day here, we got student A and student B saying goodbye and heading in opposite directions. And they walk at constant rates. So at the first day of class, I talked about understanding physics principles. You have to understand physics principles to solve problems. So as you read through this, it tips you off that they're moving at constant rates. So it's uniform motion. So if it's uniform motion, then the only formulas that I can use, or the only formula that I can use is essentially this one here, d equals vt. That's the uniform motion formula. So student B heads west, and student A heads east. Okay, and they give you both a distance and a time for both. They're both 3 minutes for time, and there's two separate displacements. So they want us to determine the velocity in meters per second. So let's take a look at part B. Let's find the velocity of student A. 300 meters in 3 minutes. How many seconds is in 3 minutes? So 3 minutes. In 1 minute there are 60 seconds. So 300 meters in 180 seconds. That is, calculator please, 1.6 repeater. Okay, so how many sig digs we got? 3? 2. We got 3 minutes here. So 1.7 meters per second. And the direction on the student A is east. Okay, so notice what I did there. I did the math, and then right as I'm going to finish off the question and communicate my answer, I scan the question, look for sig digs, and then is it a vector? Yes. So magnitude and direction. Okay, let's go find the velocity for student B. This guy goes 450 meters in the same time. So will his velocity be faster? He covered more distance in the same amount of time. So his velocity will be higher. 450 divided by 180 is 2.5, and the direction for this fella is west. Now for the graph, I would recommend that you use a straight edge tool. So I got a bunch at the front. You can also use ID cards. Now notice what I'm doing here with my grid. I have obviously my horizontal axis, which is going to represent time. But vertically, I've left space for positive and I've left space for negative. So this is a displacement time graph or position time graph, so you can put d bar there. Let's put 0 right there at the origin. Let's mark off 3 minutes. Now, which student went faster? Student B. So in terms of displacement, one of them covered more in the same amount of time. So one of the lines is going to be steeper than the other. So you can mark off 1, 2, 3. 1, 2, 3, 4, 5. And that guy is about halfway between 4 and 5. And then you can see one will be steeper than the other. Same time, different distance. It's just a sketch. Gives you an idea of a positive displacement versus a negative displacement. You have positive values going up, negative values going down. Now there is one more question to do. It is challenging, so I will leave it as a challenge. So I will leave this for you guys. We will go over it on Monday. And if you can get it, I applaud you. And if you can't get it, that's okay. We'll do it on Monday. And that'll be it for today. You can sit tight till the bell rings.